It's Friday, May 15th, and this is Nighttime Mathematics Radio. The show works the same way every night. You tweet your questions into @NightMathRadio on Twitter, and I try to answer them live here on the air. So as always, we'll take a few quick break at the beginning here so that you can tweet in your questions. Back in a minute or two. This is Nighttime Mathematics Radio. Welcome back, everybody. Hoping you're enjoying some of the strangest loops that Apple ever provided with GarageBand. So in the meanwhile, we got one question tonight, which we're going to take a look at now. This is a question that came in earlier about particle motion. So the question came in, well, how do you handle these kinds of questions? In this case, the student just missed the lecture about it, so we're not sure what to do. But the question looks like this. Let's go over to the notepad. They're given the graph of motion of a particle, which looks like this. Draw the axes here. So the vertical axis here is x, measured in meters. And the horizontal axis is time, measured in seconds. 1, 2, 3, 4, 5, 6, 7, and they go. And the graph is there. They don't really graph anything past 6. The particle starts at 3, stays at 3 till time 1, then goes down linearly to 0 by time stepped by 3 seconds, then very abruptly falls to -3. At 4 seconds. So at 4 seconds, it suddenly jumps all the way down here, very abruptly. Just bang, almost straight down. It hangs out at -3 until 5. Then by 6, it pops back up to -2. So the first question they ask is, when is the particle moving forward? When is it moving backward? And when is it staying still? You can actually see that from the graph. Remember, going forward means that your position is increasing. Because that means you're moving in the positive x direction, whichever direction that is. And by the way, be very careful here. When students are first learning graphs, one thing they do almost all the time is they always think of the vertical axis as the y-axis and the horizontal axis as the x-axis. That's not going to work here. The horizontal axis, it says right up here, is the x-axis. Sorry, the vertical axis is the x-axis. This is the position graph. The horizontal axis is the t-axis. This is the time axis. So this is a graph of x versus time. This is position versus time. So do not get confused to think x means this way. That's not what this graph is saying. So when is x increasing? Well, only for 1 second, between 5 and 6 seconds. So it's going forward from 5 seconds to 6 seconds. Backwards? Well, it's moving backwards from the first second here. It starts moving in the downward direction, which means backwards in this case, all the way through 4 seconds. When it's standing still? Well, it's standing still when the line's going perfectly horizontally, because that means that x isn't changing. That means it's staying at the same position, and time is increasing because time increases whether you're doing anything or not. So that goes from 0 seconds to 1 second, and from 4 seconds to 5 seconds. So that's what's going forward, that's what's going backwards, that's what's standing still. The second question asks, when does the particle turn around? And this isn't actually a well-defined answer, because turning around means you go from moving backwards to moving forward, and it does that over this entire second between 4 seconds and 5 seconds, because it sits and hangs still for a second before it goes the other direction. So I would probably answer this by saying from 4 seconds to 5 seconds. That's when it's turning around. Doesn't turn around at a discrete point. If this thing were smooth, if it's something like that, then we say there's the point where it turns around. It was moving downwards, then it moves upwards. But there's nothing like that in this graph. This graph is a bunch of line segments. Why is there a bunch of line segments? Because this is a graph being asked in a pre-calculus class. If this were being asked in a calc class, it would not be a bunch of line segments. It would be some differentiable function, and then we'd use derivatives to answer these questions. So this is a lead up to something that happens in calculus. How about question 3? It says, when is the particle moving the fastest? So first thing we have to ask is, what does speed even look like on this graph? What does speed look like on a position graph? The answer is, well, what does it mean to be going fast? That means that your position is changing very quickly per unit time, right? It means you have a high meters per second or high miles per hour. What does that mean here? That means that your change in position divided by your change in time is large. But then we say, well, wait, change in position is the change in the vertical axis. Change in time is the change in the horizontal axis, so let's just rise over run. So what we're saying is we're interested where the slope is big. And we can just read off what the slope of each segment is. This segment has slope 0. This segment, we fall from 3 down to 0 over the course of 2 seconds. So the slope here is -3/2. Here we fall by 3 in 1 second. So this is just slope -3. Here again we have slope 0. And here we go up by 1 over 1 second, so this is slope 1. And now the cool thing is, I described these as slopes, but because this is in meters and this is in time, the slopes have a unit. This is 0 meters per second. This is -3/2 meter per second. This is -3 meters per second. This is 1 meters per second. And they said, when is the particle moving the fastest? And you might think, well, that means the biggest one of these numbers, and 1 is bigger than -3, so that should be it. And not quite. When you ask how fast something's moving, you don't care which way it's going. You just care how quickly it's moving. So going quickly backwards doesn't mean you're going, slower than slow. It just means you're just going fast. You're just going fast the other way. So for how quick are you moving, you just care about the absolute value of these numbers. And so the particle's moving the fastest between 3 and 4 seconds, between 3 and 4 seconds, going. And if we're just saying how fast we're going, you're just talking about your speed, not your velocity. This is something they always drill into people at the beginning of problems like this. The difference between speed and velocity is the speed is just literally how fast are you going. Don't care about the direction. Just how fast did you go? Velocity does care about direction. So the velocity here is minus 3 meters per second. It's 3 meters per second backwards. It has a direction. The speed here is just 3 meters per second. Speed is what cops care about. This is why your dashboard in the car is a speedometer. It doesn't have 0 up in the middle of the speedometer, then it goes down, it deflects to the left if you're going north, and to the south if you go to the right if you're going south or something. No. This is just speed. Absolute value. So it's going 3 meters per second in that time. Question 4. What's the net distance traveled, and what's the net displacement? The difference between distance and displacement here is exactly the same as the difference between speed and velocity. The distance traveled is literally how far did you go. I don't care which direction, just how far did you go. How much, if I drove this, how much did my odometer go up? Assuming I'm not doing something ridiculous like driving backwards in an old car and hoping I can get my odometer down. So how far did we go? Well, we started at 3 and went down to -3, so we traveled 6. And then we went back up to -2, so we traveled 7. So the distance is 7 meters. The displacement, on the other hand, just asks over the whole motion, how far did we end up going overall and in what direction? So in this case, in terms of displacement, if I go too far then back up, I've lost some of my displacement. I'm actually closer to where I started than I was at the beginning. So for displacement terms, all I care about is I started at 3 meters and ended up at -2 meters, so my displacement is -5 meters, because I ended up going backwards by 5 meters. And for displacement, that's all that matters. Then finally it says, what's your average speed? And your average speed is, what distance did you go divided by how long did it take you to do it? Well, it took us 6 seconds, and we went 7 meters. So our average speed is 7/6 meters per second. Sorry. Yes, that's right. I went 7 meters. I did it in 6 seconds. So 7 meters over 6 seconds, or 7/6 meters per second. The average velocity is just like this, but this time it's the average displacement. It's how far did they go net. So this average velocity doesn't care that you bounce back and forth like crazy. It just cares how far did you go and in what direction and how long did it take you to get there. And in this case, we went 5 meters. We did it in 6 seconds net. So our average velocity is -5/6 meters per second. And again, this is assigned quantity. Speeds are always positive. You never have a negative speed. But velocity has a direction to it. So it matters that it's 5/6 meters per second backwards. There's a difference between having a velocity of 5/6 meters per second forward and a velocity of 5/6 meters per second backwards. And we capture that by putting a sign on it. And that's it for this problem. That's how you handle simple particle questions like this. And now you say, well, that's great, but to do this kinds of speeds, it was great. It was good that we had line segments, because if these hadn't been line segments, we wouldn't have been able to do anything. If this had been some general curve like I do over here, how would we ever know our velocities? How would we ever know how fast we were going? And the answer is, take calculus. That's what calculus lets you do. Calculus basically lets you answer that question. And this is Nighttime Mathematics Radio. Well, let's see. Looking at Twitter, I don't see any new questions asked today, so it looks like we're going to end the thing right there. Now, unfortunately, next week, daytime non-mathematical employment has become very, very busy. Next week, it's not clear to me that I'm going to sleep, so day will become night, night will become day. It'll be a bad scene. So the next Nighttime Mathematics Radio will air a week from next Monday. So a week from next Monday, I'll be back bright and early, ready to start Nighttime Mathematics Radio. That's on Memorial Day weekend if you're in the United States. So I'll see everybody then. That's Monday, May 25th. Until then, feel free to keep tweeting me questions. I'll keep answering them online. Keep doing the math. Stay safe, everybody.